How is everyone? All 10 of us.
Doing pretty well, Nick. How are you doing?
Awesome. Glad to know people are out there. All right. Any questions? All right, let's talk about PA3. So I posted this on Canvas last night. So PA3 is going to deal with stacks and queues. And I'm not going to give you a programming assignment on hashes, at least not for this class. But you should still know about hashes. They can still show up on exams. But PA3 is going to deal with stacks and queues, and you're going to work with stacks and queues implemented using linked lists. All right, so you get to reuse some of your PA2 code. So let me show you sample execution. And I've given you a sample program on the Linux server that you can use to play with this. So it's /temp/PA3. And if you're unsure what the program is supposed to do, what it's supposed to output, how it's supposed to respond to certain situations, you can run this program, and this adheres to the requirements of the assignment. So run the program. It's giving me a welcome message, optional usage message up front. It's kind of nice to do sometimes, but welcome the person to the program and so on. And then basically you have two data structures underneath. You have a stack and you have a queue. Okay, and you can manipulate these. Well, what do you do with stacks? You push and you pop. What do you do with queues? You add and remove. That's really it. Okay, but you got both of them available here. And so the program has a notion of state. It can be in one of two states or modes, stack or queue. And it begins in stack mode. Okay, that's important. So right now I am ready to interact with a stack. And if I want to add something to the stack, it's a stack of numbers, I just type the number and hit enter. And assuming nothing goes wrong, it doesn't do anything except come back with another prompt. Okay, so no additional feedback, number was added to your stack size is such and such, nothing. Okay, just come back with a prompt. It's silently doing what I ask it to do. Let's push a 9 on the stack. Let's push a -77 on the stack. At this point I should have a stack with 3 things on it. -77 should be at the top, followed by 9, and followed by 234. Okay, the S command will show me the contents of the stack. So TOS is top of stack, that's on the left with an arrow pointing to the number that's at the top of the stack, followed by the other things that are in the stack separated by spaces, and then just come back and give me a prompt. Now the S mode is also how I get into stack mode if I'm in queue mode. So I'm also printing a kind of redundant message here, switching to stack mode. You don't have to do that. If you want to suppress it, you can. But if you're in queue mode and you say S, I want you to tell the person you're switching to stack mode. So first order, easiest approach, just always print that message when you type an S, and then show the contents of the stack. Now if you want to remove something from the stack, that's the P command, that's for pop. So when I do pop, 2 things happen. One, this -77 will be removed from the stack, and 2, the program will show me the value that just got popped. So P shows me -77 and comes back to a prompt. And if I want to see my stack now, I can type in S and I'll see it's just got the 9 and the 234. And if I pop again, it'll show me the 9 that got popped, and now the only thing on my stack is a 234. And I can push an 11, and now if I look at my stack, there's an 11 sitting on top. And the poor 234, which was the first thing that got pushed, is still waiting to be popped. And I can put a bunch of things on my stack, and now those are all stacked on top of my 11 and my 234. So I can start removing those. And now I've just removed the 11, and if I look at my stack, I got one thing left, the 234. If I pop that, there's my 234. Okay? The stack is empty. No additional messages get printed here. Okay? I popped off the 234. Show me the 234. If I use the S command to see what the stack looks like, now you can say the stack is empty. And now if the stack is empty and I try to pop, that's an error condition. That's a stack underflow. Print a message. Stack is empty. Don't do anything else. Don't like zero out memory or delete files or anything like that. Stack is empty. Everything continues as usual. If I want to put something into the stack, let's put a 2 in there. Now I've got a stack with a 2 in it. If I pop that, there's my 2. The stack is empty. If I push in a 5, now I've got a 5 in the stack. Pop that, the stack is empty. Try to pop again. There's my error message. If the stack's empty and I try to look at it, it'll tell me the stack is empty. Okay, any questions about stack mode? About what's going on here, what all of this means? Stacks can have as many copies of a number as you like. Not a problem. They can be negative, they can be positive, they can't be ha-ha. No problem, you're here, that's what counts. There is no inherent size limit to this, so you're using a dynamically allocated stack linked list that you're building with malloc, so the limit to the size of the stack or queue is the amount of memory that you're able to malloc one node at a time. So it's essentially unlimited, and I won't try to blow it up. But you know, I might insert 1,000 nodes and make sure that you don't have some sort of artificial limit. All of these things, right, for the most part, we're trusting scanf to tell us, you know, what's a valid integer. So if I put in some weird number like that, right, scanf will do something with that. In this case, it turned it into a -1. I don't know why. But whatever scanf does, right, take that. So I'm not going to test it with an illegal integer, with, you know, a very big integer, but I'll test it with something like that. Hope that's illegal. That's legal. So don't worry about taking the input as characters and seeing if it's too big to fit in an integer or anything like that. I'm also not worried about, you know, if the person says 12, ha ha ha, I'm just going to take that as a 12. Right? As scanf takes it, I'll take it, basically. Alright, any other questions about stack mode processing? Do we go through the whole linked list to get to cache? How is it integrated linked list? What do you mean to get to cache? The hash. There is no hash. This assignment has nothing to do with hashing. This is strictly stacks and queues implemented with linked lists. Alright, so you can also interact with your queue. So the queue command switches you to queue mode and shows you the contents of the queue. Right, the stack and the queue are initially empty, so when I switch into queue mode, I see an empty queue. So I've got the word head over here on the left with an arrow, which would point to whatever's at the head of the queue, and then separated by spaces all the elements of the queue, followed by an arrow which points to the tail and the word tail. So let's add some things to our queue, and we'll just add them in order. And now if I look at my queue, you can see what the setup is. The first thing that I added, that's what's sitting at the head. The last thing that I put in is sitting at the tail. And now if I remove from the head of the queue, which is again the P command, it should give me the 1. That's the thing at the head. And removing again will give me the 2 and the 3, and now if I look at the queue, the head of the queue is pointing at the 4. Alright, and I can go back to stack mode, and my stack is still there. Nothing's happened to it. No harm has been done. It's still got the data that was in there. I can, add some more things to my stack. Go back to queue mode, and my queue is still intact. So they're completely separate data structures. And switching modes between stack and queue mode doesn't change what's in the data structures. It's just changing what our main program does. Alright, so I can remove the 4 and the 5 and the 6, and now my queue has one thing in it, which is a 7. If I remove that, again, nothing special happens, just remove it and show me the value that you removed. But in fact, the queue is now empty, and if I say queue to look at the contents of the queue, I'll see my empty queue, and if I try to remove from an empty queue, that'll give me an error message. Alright, any questions about queue mode behavior? And we're going to talk about implementation and grading and all that stuff next. So since these are implemented using linked lists, yes, you're going to want sentinel nodes pointing to each list. And you're going to have 2 completely independent data structures. So 2 linked lists, 2 sentinel nodes. Yeah, you're welcome. And these commands are the same whichever mode you're in. If I type a number, sometimes that'll insert it into my queue, sometimes it'll push it onto my stack. If I type P, sometimes that'll pop from my stack, sometimes it'll remove from my queue. So you're going to have to do a bit of stateful programming. You're going to need some notion of state. Right? What is the current state of the program? Is it in stack mode or queue mode? And then when you're parsing your input, respond to these based on what state you're in. So P doesn't always call pop. Sometimes it calls pop, sometimes it calls remove. How do you know? It depends on your state. So what is the state? It's just an integer. Yeah, it's basically a flag. So make yourself, a state variable. You can call it something fancy. And decide how you're going to represent the 2 states. Maybe stack mode is going to be a 0 and queue mode will be a 1. Or maybe, I'll use 17 and 55 for my 2 modes. Something. And then when you parse your input, let's say we parsed and we just found out that the person typed in an integer, what do? Well, if my state mode variable is equal to, the stack value, then I'm going to call push. Otherwise, I'm going to call add to push into my stack or to add to my queue. And you can make good use of defines here to avoid magic numbers. You could set, state mode to be 0 and queue mode to be 1, but, somewhere along the way you might get confused and start thinking that 0 is queue mode and 1 is stack mode. So you can use some defines, right? You can say something like, define stack mode 0, define queue mode 1, and then somewhere in your code, let me call it mode. I'll define my mode variable. That's my evil global, keeps track of state. Doesn't have to be global, it could be in main. That's my state variable, and I'm initializing it to stack mode. And then somewhere, got an int. So if mode equals stack mode, push my integer, or else call my add routine, and so on. Alright, so that's kind of a new twist on our program, but it doesn't have to be a lot of heartache. Alright, so that's what the program looks like, and you can run this yourself, so Q gets you out. So it's /temp PA3, and you can run it under Valgrind. It shouldn't give you any memory issues, no warnings, no memory leaks. All right, so let's look at the assignment in detail. So you have to implement your lists, your stack and queue with linked lists. Okay, not with arrays. And you need to use linked lists in the style of PA2. Now, if you rewrite them from scratch, if you decide not to use a Sentinel node, things like that, I'm okay with that. But you're not allowed to go back to PA1 where you were using an array. Okay, it's got to be an implementation using linked lists that are dynamically allocated in memory, using malloc and all that kind of stuff. All right. Your program has two distinct structures. There's a stack and a queue, so two separate linked lists. Okay, don't combine them. They've got to be two separate linked lists. And then your program works in two different modes. All right, here's the command summary, but we already saw what these commands do. So S says, print the contents of the stack and change to stack mode. Okay, stack mode meaning interpret these commands from the view of the stack. But also print the contents of the stack on one line, separated from spaces, with the top of the stack at the left. Don't show me the Sentinel node. Okay, gotta have TOS on the left, not the right. And that's going to be the natural print order anyway. Queue will go into queue mode, print the contents of the queue, also on one line. Head of the queue on the left, tail on the right. Gotta be in that order. Okay, if the tail's on the left, I'll take off points. Any legal integer, either push it onto the stack or insert it to the tail of the queue, depending on what mode you're in. P will either pop the top of the stack or remove the item at the head of the queue, and then print out the value that was popped or removed. Q will quit the program after making sure that it frees all memory. So you're using linked lists. Before you exit your program, you got to free the memory in those lists. When you pop or remove, that's like doing a delete. You're basically removing a node from a list. You definitely want to free that memory at that point. But when you're done, you've got stuff sitting around in memory, you got to free that also. So use the free routine that you did in PA2 basically. Uppercase Q exits the program. Anything else gives a help message. Please don't produce any additional output. Don't show me success messages. Don't keep showing me the command list, things like that. Those will all cost points too. Okay, implementation. So two linked lists. Your stack, supposing you have a Sentinel. First node is your top of stack. That's where you're going to insert. Your queue, Sentinel node. So the node right after the Sentinel, that's the head. The last node in the list, that's the tail. So we push and pop from the thing right after the Sentinel. For a queue, we add at the tail, we remove from the head. and you got to do it like this. And this simplifies your main program, right? Having the top of stack here, well, when you want to print your stack, you're basically just moving down the list, printing each node in order. And the first one you print is going to be the top of the stack, which is what I want to see on the left side of your printout. When you print the queue, just move down the linked list in order and print each node, which is going to print the head first and the tail last, which is the correct order. So do them like this and everything works out great. If you switch these around, you're going to have a lot of extra work to do. This also makes it possible to have a tail pointer, which always points to the tail, because when we want to add something, we can get to the tail right away. We can add our new node, and then we can set tail pointer to point to that new node. So to add, you don't have to march all the way down the list. You can use a tail pointer. If you don't do that and you just decide to start here and move till you get to a null, I'm not going to take off points for that. Okay, but that's going to be an implementation that gets really slow as your queue gets large. So try to do it with a tail pointer. Alright, so for the stack, push new elements by adding a node immediately after the sentinel, pop from the same queue, remove from the head, which is right after the sentinel, and insert at the tail, which is at the end. Okay, you should not run out of memory. I won't try to make you run out of memory. If something happens, though, right, when you call malloc, if malloc happens to return null, that's a catastrophic condition. Don't just ignore it. If you ignore it, you'll segfault. So if malloc returns null, you can do something like, either abort the instruction or say, system is out of memory and exit the program, something like that. It's not going to come up, right? But you should always check the return from malloc. Okay, I will try to underflow your stack and pop from an empty queue though, right? So just print a message and life goes on. Don't delete the structure or anything bizarre like that. Okay, it's an acceptable condition to try to pop from an empty stack. Just say stack is empty. So if you're going to do a tail pointer, then you need some way to keep track of that, and I would put that in your collection of queue objects, or you could put it in the sentinel node, which would put it in every node. It's up to you. If you keep track of it outside, you would have to use an evil global, which I don't recommend. So I would actually make it part of the node. And it wastes a little bit of space, but we're not worried about it. And so now the sentinel would have a field called tail pointer that we would use to get to the tail. These other nodes would have the same field, and we just wouldn't be using it. Just like we don't use the data node in the sentinel, the data value in the sentinel. These can be struct nodes, or they can be anything else. They could be struct queue nodes or struct stack nodes. Or whatever you like. Which brings us down to the program structure. So program structure, I'm giving you more or less complete creative liberty here. Okay? I'm not giving you a set of functions with prototypes. I'm not giving you a particular structure with fields. I'm leaving it up to you. Right? So number one, this is more fun for you. Number two, I want to see what you come up with. Right? And you can certainly, bounce things off me. You can ask. You can say, here's what I'm thinking of. You can discuss this with other people in class, right? I worked this through and I only found 3 functions. Does that seem right? Or, I came over the list of 55 functions I need to implement. That seems like too many. What did you do? Okay. We're not talking about comparing code, but if you want to talk about how you're structuring the program, what your functions are, what you're passing to the functions, where you're storing a tail pointer, that's all good stuff to collaborate on. Okay? What I don't want you doing is sitting down and writing code and then sharing code with one another and taking somebody else's code and using that to write yours. But a big piece of this is sort of the higher level organization, figuring out how we're going to break this into a set of pieces. and how those pieces are going to work together. And I want you to get some experience with that. Okay, as we move forward, I will generally give you less and less structure in the assignment itself, and I'll leave that to you to come up with. And making these choices, right, this is the essence of learning data structures, is figuring out how do we want to organize all of this information. So can linked lists only contain a data and next variable? Nope, you can make them however you like. You can put in extra things. You could make a doubly linked list if that helps you. I don't think it'll help you in this one. Right? As long as you're implementing your stack and queue using linked lists that are actually dynamically allocated. So you're using malloc. So don't take my offer of creative liberty here and, you know, implement the stack with the cell phone that calls your friend and says, write down this number for me. Don't do that. That would be a cool implementation, though. I'd like to do that sometime. But yeah, so let me give you some suggestions, and these are just mostly to help you understand what these kinds of things might do, rather than saying, you know, this is the best way to do it or something like that. So I suggest you have a clean implementation of linked lists, similar to what you did in PA2. Don't be writing a stack push function that's also got code in it for doing, you know, malloc this, and here's a next field and loop until it's equal to null and all that kind of stuff. Get some separation in here, right? Start with a linked list library that you've written. Hopefully your PA2 code works for that, maybe with some minor tweaks, right? But have a collection of functions for, you know, inserting into a list, removing from a list, you know, traversing a list, that kind of stuff. And you'll need to do a little bit of tweak on PA2. For example, our insert function does not sort. We always insert at the beginning, right? For a stack, we always insert at the end for a queue. But those are subsets of your general add function from PA2. So my suggestion, make yourself a nice clean implementation of linked lists, and then start taking, start working on stack and queue code. Can they both take inputs that match, like 2 1s? You mean, can you have the same thing more than once in a stack or a queue? Yes, absolutely. No restrictions on that. And when you add something to a stack, right, there's never any need to do anything other than just make a new node, point the sentinel to it, point the new node to this. When you add to a queue, just go down here, point that to the new node. New node points to null. And completely agnostic to what else is going on inside the structure. Alright, so I also suggest making a set of stack routines. Initialize stack, push pop, is the stack empty, and display the stack. And a set of queue routines. Initialize the queue, add to the queue, remove from the queue, is the queue empty, display the queue. Some of these are going to look exactly the same. What do we have to do to initialize a stack? We have to create an empty linked list. Well, that's just your init function, right? So initializing the stack is really just a wrapper around calling your linked list's init function. And initialize queue is exactly the same thing. And if you're only using one type of node, right, say it's a struct node, then your stack is going to be a struct node star. And your queue is going to be a struct node star. But if you have 2 types of nodes, the struct stack node and a struct queue node, then, you know, your stack and queue will be a pointer to the appropriate type of structure. Display stack, display queue, probably exactly the same code, right? My main program I would make responsible for printing out, you know, the special message if the structure is empty, or, you know, if I'm doing a stack, print out the TOS and then the arrow and so on. But to go through the structure and print out the actual numbers separated by spaces, that's the same whether you're doing a stack or a queue. And if you implement your structures like this, it's exactly the same linked list algorithm. start with the thing the sentinel points to, print that value, print the next value, just go through until you're done with the last node, print out those data values separated by spaces. So you can jump into this and start writing code and get to a few hundred lines of code pretty quickly. But if you spend some time before you do that thinking about how to structure this, you might find this takes very little code. I just checked and my PA3 is horribly long, but I put in lots of comments. So think about the organization of your program, and my suggestion would be to write this, forget about the main program, forget about queues, start with stacks. Well, get your linked list system in shape, right? And make sure that, you know, it's a nice clean implementation. Remember, you're going to have two linked lists, so if you did anything kind of funny in PA2, like you used an evil global to store the Sentinel node, that's not going to work here, right? Your Sentinel should be a program that's in your main program that you give a value by calling a init. So here you're going to have two Sentinels. We're going to call init twice. But start off, just work on your stack, right? So you've got a linked list package. Make an initialize stack function. What does that do? It just calls initialize list. Save that stack value somewhere. Make a push function. Okay, push is about 4 lines of code. How do we push the number n onto our stack? Make a new node with data value n. Set new node next equal to sentinel next. Set sentinel next equal to new node. You're done. So make a push function and then make a display stack function, which just goes through and it basically does your print function from PA2. But now what can I do? I can initialize, I can push, I can display. Now exercise that with your main program. So do something like this. Right, so that initializes an empty stack. Push my stack, push a 5 onto my stack, print out my stack, where this is my stack print function. Push a 10, call my stack print function, and so on. Right? No scanfs, no fgets, nothing like that anywhere in sight. Just write something that exercises your code. And this is nice for a few reasons. One, it gets you into the gushy stuff quickly, right? 224 was all about, you know, parsing and scanning and fgets and stuff like that. Presumably you can do that, right, given proper circumstances. This is the stuff that's potentially new, right? So let's get into this part sooner rather than later. Otherwise, you know, you spend a bunch of time working out the details of parsing and scanning, all that kind of stuff. You finish that, you're exhausted, and you haven't done anything with stacks and queues yet. So start with the part that's probably new, right? Write some stack code, and I'm just testing it with some hardwired test code. And if I do this and it doesn't work, when I try to do my sprint I get a seg fault, I've got a test case now that blows up. I don't have to type anything in to make it blow up. I just run this and it blows up. Well, now I can compile with -G, I can put it in GDB, I can say run, and I can see what happens. And if I decide to change my print function for something else, right, and I want to test those new changes, say make, say main, and it'll run my new program. Don't ever call your program test, though. It's a keyword. All right, so that's my suggestion, right? Do your initialization, push, and then display. once that works, go ahead and add pop. And now in your test program, do a few pops and some prints. And then throw in a stack empty function, maybe just print that out every time that you pop and make sure that's working. And now my stack code's done. And I've dusted off my linked list code. I've got the extra capabilities of the stack, and you know, the push is like 3 or 4 lines, the pop is about 3 or 4 lines. Stack empty is 1 line, see if the sentinel next is null. Display stack is a variation on your print from PA2. And now work on your queue. Well, your queue is slightly trickier because you've got 2 ends to deal with. When we want to remove, we still just go right after the sentinel and pull off that node. But when we want to add something, we got to get to the tail. So either use a tail pointer or a traverse to the end. So that takes a little bit more work, but it's not too bad. And then same thing, test some adds and some displays and some removes and so on. And then once you got this stuff working and you're pretty sure all of these functions work, now switch to 224 mode and work on your program, your main program, which is parsing. But it's stateful parsing, right? To understand what S should do, we need to, or to understand what P should do, we need to know what mode we're in. But that's kind of fun to nail out. And then worry about memory leaks. So when you pop or remove, free the memory right then, but then also when you do a queue, call whatever your linked list removal memory freeing function was. So you probably want some other functions in here, including like free stack from memory or something, and free queue from memory. All right, questions on that? So deliverables, complete implementation of a linked list based stack and a linked list based queue. Right, everything we've been talking about. Main program as described above, as demonstrated, and you can run /temp/pa3 to see a sample executable. Okay, and try to stick to that behavior. Plenty of commenting in your code. Okay. Very, very important here, since I'm not giving you definitions for functions, I'm not giving you prototypes, you need to document it. Okay, and your documentation should probably look something like this. Let's say we're doing a let's say that's the function that we're implementing. Okay, here's what you could do before that, right? Push, add number to top of stack. Arguments. Struct node stack, pointer to sentinel. Integer num. Number to push. Return value, none. Possible errors, out of memory, you know, causes the universe to collapse in on itself or something like that. So I'm not mandating this, but find a style that you can be consistent with for documenting each of the functions that you develop. And if you're consistent about it, you can use this when you're writing your code. Because you're going to write a set of queue functions, a set of stack functions, a set of linked list functions, and a main program. By the time you get to your main program, you don't want to have to be reading through your code to figure out how you call your push function, right? So if in your code you have some sort of, block of asterisks or something that marks off the comments with a standard organization that you can look at and say, okay, yeah, I passed the pointer first and then the number, right? And does this return anything? Should I check the return value to see if there was an error, right? It will help you with developing. So play around with that, right? And let this be part of your programming style that you're developing or that you've developed, how you're going to do this documentation, right? But I want this information before every function that you write. Let's see, I don't mean to ask a stupid question, but how do I know where I should comment and where I don't need to? It's a really good question. It's a bit of a balancing act, and I'm erring on the side of wanting lots of comments in this course. Okay, it's easier to get out of the habit of commenting than to get into the habit. But basically, you want your commenting to explain why you're doing something, right? You don't want to make obvious comments that I equals I plus 1, comment, increment I. Well, that doesn't really tell you why you're incrementing I, right? But I equals I plus 1. Keep track of how many inputs we've processed. Okay, now I know what I equals I plus 1 is doing. It's counting the number of inputs. So I wonder if I can easily find some code. I don't know. So this is just like some sample code for PA2, right? Let me try something different. Here's some sample code from PA1. We'll go with that because we're not redoing PA1. Routines for managing my list. So here's the init function, and it takes the struct node array and sets up element 0 as a sentinel. Then sets all other nodes as free by setting valid equal to 0. This creates an empty linked list, sentinel only, arguments, list the array of nodes, return value none. And then here's the function, right? So there's my declaration, list 0, next is my null. Well, I know what that's doing, right? It's setting the next to my null, and up here I said, I'm creating an empty linked list, setting valid to 1. I'm setting data to 42. Why? Because I'm just using that as a flag, so if I bump into the sentinel, I'll know it. Now I have a loop where I say, I equals 1, I less than 100. I could put a comment here saying, do this for I for all values between 1 and 99. But that's pretty obvious from looking at this statement what that's going to do. But what I'm doing inside that loop is I'm setting an element's valid flag to 0. Why am I doing that? Because I'm making that node available. And in fact, in this loop, I'm setting all nodes to be available. So it's you don't necessarily need a comment on every single line, but it's not impossible to imagine that you might want something close to that. Right? So here's my add function. I'm searching for where I should insert my new node. That's what this while loop does. Right? So I'm describing what this whole block of code does. This block which is indented to stand it apart. And inside here, I'm doing a while loop. I'm checking to see if my current data is bigger than the thing I'm inserting. And if it is, I'm about to do another block of code. What's the purpose of this new block of code? Insert between the previous and the current node. And then what do I do in here to make that happen? Right? Point the current node to the new node points to the next node, and then return success. And sometimes it's nice when you get nested to, like, you know, tag what these closing curly brackets are. This was the end of the block that inserted a node. Otherwise, move down the list. So, you know, try to find a balance, right? Printing is not a terribly complex routine. You basically move down the list and print. But I still like to know, you know, what I'm doing here. I'm setting PTR to be the first data node, right? As opposed to the first sentinel node. And I'm also noting in here, this could be my null. So now I iterate while the pointer is not my null. I print it out. I move down to the next one. And little comment here that there's a trailing space that you won't see, and then print a new line. So experiment with it, and if you want some feedback, right, come by office hours and we can go through code and discuss, you know, too much, too little, right amount. But like I say, erring on the side of too many comments, that's a good problem to have. All right. Let's see, so deliverables, plenty of commenting, comment block in the beginning, proper make file, which makes an executable named PA3. That's got to be the executable name. That should be the default behavior of make, and make clean should be an option to get rid of all the compiled code. Push this to GitLab in a repo named stacks queues, uppercase S, uppercase Q. 24-hour offer. Do this before noon on Friday, tomorrow. Send me an email and ask me to check it, and I'll download your repo, let you know if it works. Grading rubric, 20-point deduction if it's not turned in on time, and then you have 24 hours to get it in. If I can't compile or run it, if it's seg faults, etc., that's 40 points off at least. If it's not doing the assignment, that's a 0. Okay, so it's got to be doing dynamic linked lists to implement stacks and queues. Specific points, proper makefile 5%, working push and pop 10% each, 5% each. Working queue add and queue remove 5% each. Correct management of program state, switching from stack to queue 10%. Keep in mind, for example, if you can't change from stack mode to queue mode, I probably can't check your queue add and remove, so you're going to lose points there also. Correctly printing the stack and queue contents following an S or Q command 10% each. Okay. Main program works as required, the proper commands, proper amount of output, and so on and so forth, that's 10%. No memory leaks or errors or warnings from Valgrind, 10%, so keep up the work on that. No compiler warnings, 5%. Function comments, 5. Comment block in the beginning with your name, assignment, description of the code, 5%. Comments throughout your code, 5, and consistent indenting, 5%. So very similar to the previous assignments. Any questions on that? All right, so take a look through that. Bring questions to class tomorrow, and tomorrow I'll make a few comments finishing up talking about iterators, and then we're going to switch to talking about binary trees, and that's going to be a major topic, so we'll spend a few weeks at least talking about binary trees, and it will be an embellishment on linked lists basically. So we'll start from there tomorrow. Have a good afternoon. I will see you next time.